All right, Z-scores and quantiles, baby. Crash course. This is the queen mother. What Z-scores are good for, they're standard normal distributions. So not all distributions are a standard size. They might be distributed somewhat normally, but they have different properties, different inflection points. And what a standard normal it does is make them one perfect bell curve that you can compare different things to. So, for example, Christian just took a chem and bio exam. He got a 76 in chem and a 81 in bio. And so obviously in bio he did better for himself, but compared to the rest of the class, which one did he do better? And I can't really tell from just the mean and just the standard deviation. And so what we can do is compare z-scores, which means number of standard deviations away from the mean. And we did it like this. So z-scores compares a data to the mean using standard deviations. Again, how many standard deviations is this point away from the mean? So it's a lot of scary looking math, but really the z-score is your score and the difference between your score the difference between your score and the mean divided by the standard deviation tells you how many standard deviations from the mean you are, above or below. If it's positive, it means you're above the average, and if it's a negative z-score, it means you're below the average. So may your z-scores always be positive, but they can't for all of you. So Christian just took, this is the same idea. We want to find his z-score in chem and z-score in bio. All right, so looking at his z-score in chem, he got a 76. Here's the mean, here's the standard deviation. Right, so the difference between his score and the mean divided by how big a standard deviation is gives you this 0.531. That means it's positive, so that means it was 0.531 away from this average, the mean. Right? So if you kind of visualize this curve, and this was the average, if you turn these all into a normal standard distribution, he is 0.5 away from the average in the positive direction, 0.531 standard deviations, which means the standard deviation is almost twice as long. In bio, you can do the same thing, but we're going to compare its specific numbers. So here's his score, the class mean, and the standard deviation. You do the same thing here and look at the distance between his score and the mean divided by how big a standard deviation is in that class, and there's his z-score. Means his standard normal distribution. So he's not quite as far above the average in that class. Z-scores fundamentally are how many standard deviations away from the mean. So if you have a z-score of 1, you're 1 standard deviation away from the mean. If you have a z-score of -2, you're 2 standard deviations below the mean, although none of you should be. And so you can convert a z-score. You know, a z-score is really just mu plus 1 standard deviation. A z-score of 2 is mu plus 2 standard deviations, right? A z-score of 0 means you're at the mean. And we can play the same game with turning any score into a z-score. All right, so we can take normal average and your raw score. Right, so this is like raw data, and we can turn it into a standard normal by turning the average to 0, setting the average to 0, and then therefore making a z-score out of this by basing it on the mean using this concept. That's what we're going to do here. So the probability density function is this. It's not an equation that we're going to use or know, but this is what's programmed into your calculator so it can understand pieces of the probability and tell you about them. All right, before we get too ahead of ourselves, I want to look at quantiles or k values. It's just the boundary, the highest boundary that borders an area of given probability, right? So we've done this with inverse normal function. It's just called a different thing to confuse you or something like that. So here's an example, like on a exam, the mean score is this, and here's the standard deviation. Mr. Wexler initiated a plan that the lowest 80% of the students have to come in for summer school. So what's the fewest points you can get without going to summer school? So I want to know, I know that if this area is 80%, I want to know what this value is so I can stay up here and not have to go to summer school. Sweet. So we can do that by saying, I know that this inverse normal function will work to find us this value. Remember, it was like we found this probability, and it gave us this maximum x that was possible. And we can do the same sort of thing with this. You can use inverse normal. This is your probability. This is the area. This is the mean, mu, and this is the standard deviation. Right? And just run it through your calculator, and it says you have to get an 83. Let me not write this as percent just so I don't confuse you. This is 83 marks, maybe, or score, a score of 83. Cool, so that's this value is an 83. 83 marks. If that doesn't look familiar, check out my previous video on normal distributions. Alright, so this is kind of like the culmination, the tricky part, looking at converting z-scores to, or converting raw scores to z-scores. It helps you find unknown mean or standard deviation. So you're going to have to do this trick whenever you're looking at unknown mean and standard deviation. Here's the scenario. You've got a mean score on a test of 82 marks, unknown standard deviation, and we know that 75% of the scores are below an 86. Excuse me. So if we visualized this, it would look kind of like this. Oh, that's a terrible curve. That's a terrible curve too, but we'll go with it. The mean here was 82. There's a sum value here which is 86, and 75% of the test takers were below that average, or below that 86 score, sorry, not the average. So there's that component. All right, that's just to be able to visualize it. Maybe that'll help. So since we don't know the mean or the standard deviation, we can use the z-score because it standardizes all over the curve, and we can do that because we know the probability with x being, with our values being below 86 should be 75%. That's what this means, right? But if it's standardized, what that means is our z-score should also be equal to 75% of the curve, right? So we can change our raw score to a z-score by using this concept. And then we can plug in what we know. We know that the value, that our threshold value, 86, minus our average value, 82, divided by the standard deviation, that gives us our z-score. And the probability that we have less than below that z-score is 0.75. It should be the same curve. It should be the same distribution of people. It's just this one happens to be standardized. And so we're just talking about it in a different light. That's kind of a big jump. But from there, we can say that the distance between our average and our threshold value is 4. We can turn this, instead of talking about this is relating to the raw score. So we're going to have to turn it into a z-score by taking the inverse normal. And the inverse normal will tell us in a normal curve, and we make it be a normal curve because we make it have 0 for the mean, and we make it have 1 for the standard deviation. And we say, hey, I want 75% to be less than these values. Where's that value? And 0.67 becomes our new location. Right, so I know that 4 over our standard deviation should be 0.67. And what that really means is that if you multiply this over, this will turn into 4 is 0.67 standard deviations. So what that means is the distance between our average and the threshold value, that distance is 0.67. It's 2/3 of a standard deviation away from the mean. When you multiply this piece, divide over, you say 4 divided by that, you get that the standard deviation is about 6. All right, so let's try that. The same thing. We want to find the mean and the standard deviation of normally distributed random variables. The probability that you're less than this threshold value of 20 is 0.1, and the probability that you're above this threshold value of 29 is 15%, so 10% and 15%. I think the hardest thing is visualizing that. All this stuff means is that we have a probability distribution. Here's some threshold value at 20, and 10% of the population is below that. And here's some threshold value at 29, and 15% of the population is above that. So what we're going to have to do is look at a z-score for this and separately look at a z-score for that. And let's go from there. So we know this is normally distributed, so we can use these techniques. We can say that I know that below this threshold it's 10%, so let's find the z-score. Well, the z-score is based on the mean and standard deviation, and so you can set this, they went from here to here, you can set this into a z-score by saying, let's see, I want this same idea. Oh. You'd say, all right, I want a normal distribution. I want 10% to be below. My mean is 0, and my standard deviation is 0.1. And if you run that through your calculator, you get negative 1.2815, blah blah blah. You get this, right? So this piece gives you that. What that allows us to do is stop talking about the individual raw data and start talking about the normally distributed data. And then we can take this and turn it into a system of equations, because we'll have one for this side and one for that side, and it'll look like this. You'd multiply sigma over to this side, and so this would just come over here. And that's what this is. We have two variables and only one equation, so we're going to have to make one for the other side and do the same sort of thing. You can say, I know that on this side, this is a little tricky too, that this is 15% from here up, so from here down it must be 85%, right? The inverse normal only gives you to the left, that way of your threshold. So we have to think about that when we're working with this. I know, so that's where this 85 comes from. It comes from this 1 minus 0.15 is this piece. So I want to turn the raw data into a z-score, and I know that the z-score really is the distance between the average and my threshold value divided by the standard deviation. If you do this piece, but instead of 0.1, you will use 0.85. You do the same thing, and I got 0.85. 0.103. Great, I got that too. So we get this value from here, and that lets us talk about the normally distributed scores. We multiply sigma over and we get this equation. So now we have two equations and two unknowns. We could solve with a system of equations, and you end up with mu is 25 and sigma is 3.88. That's brutal, man. So there you go. Those are your solutions for that. It's hard to work your brain through that, but the big jump is going from the raw data to the Z-score, replacing the raw data with the Z-score. Give that a shot. We can do a few problems if you like. See ya.